Hello, my name is Ozgur Gursoy. I'm doing business development at imec IC Link. Before I start my presentation, I would like to thank ARM for giving us this opportunity. Today, I will talk about the challenges and constraints and potential solutions of silicon realization of large SoCs utilizing advanced FinFET nodes. So as we all know, the planar or the bulk CMOS has been continuously shrinking down. So this made it possible to develop highly integrated, highly functional and sophisticated SoCs. But there was a limit of this device scaling down, especially on the leakage side of it, that as we go down on the size on bulk CMOS, we started to see way more leakage currents, which pushes the limits of the overall power budget. So the high performance market demand made it possible for our industry to develop a new technology, which is called FinFET. So this FinFET technology is being used by those markets like AI, like 5G, like high performance computing, high speed networking in a very efficient way. The FinFET has its own benefits, very high performance features. It is not a very straightforward process to switch from bulk CMOS to FinFET. And in this presentation, I would like to provide to you those potential challenges. And one thing that I need to mention is that this know-how, this expertise in designing FinFET in SoCs mostly are available in large corporates, where those corporates are using this know-how and capability for their internal products or product roadmaps. But this is, I mean, the good news is that they are not the only one. Like imec IC Link and with our partners within our ecosystem, ARM and TSMC, we are ready to support all the startups to step up for the FinFET technologies. So briefly, I would like to give just a few words on the structure of the bulk CMOS versus the FinFET. On the left-hand side, you can see the 2D structure of this mainstream CMOS transistor. The important thing to notice here is that the control of the device is being executed by a 2D layer, where on the right-hand side, where we see the FinFET device, this control is being done by wrapping around the fins, the channel, which gives a better yield performance and better power efficiencies. So who are the main foundries who provide, who offers such FinFET technologies in a commercial way? First of all, it's TSMC, because TSMC is kind of the market leader for manufacturing FinFET wafers, FinFET chips. So they are offering 16 nanometer, 12 nanometer, 7 nanometer, and 5 nanometer commercially available process nodes. And starting from next year, 2022, they will be offering 3 nanometer as well. Other than TSMC, there are Samsung, UMC, CMOS from China, and Global Foundries who are also providing FinFET nodes on 10, 14 nanometer range. So I call this the change of paradigm in SoC design using FinFET. In this graph, I just would like to show you the mainstream node starting from 0.35, it goes down, the scaling down continues until 2012, 2013. And I put a line here where I state that the change of paradigm starts here, meaning that before the FinFET, before the technologies of 28, 22 nanometer, the dynamics of developing an SoC and ASIC was more or less the same. I mean, we would be able to use almost the same approach for 28 nanometer and for 0.35 nanometer from the manufacturing point of view, EDA point of view, design approach point of view. But when we switch to the FinFET nodes, the dynamics has slightly changed, and I will be putting some explanation, elaboration on those different items in the next slides. Okay, let's start with the design. So what are the challenges or what are the differences between the bulk CMOS and FinFET technologies? From the RTL or system and architectural design point of views, it's more or less the same, because the RTL or the system design for those phases of the design, it's kind of the process independent. Maybe the functional verification became a little bit sophisticated due to the nature of the SoCs. Utilizing FinFET, they are more complicated, so you would need to spend more time on the functional verification. Also, same for the DFT, design for testability. You need to add a little bit more sophisticated testability features. But the main change has happened on the physical design of the SoCs. Physical design meaning the layout, placement, and routing, and physical verification. And the reason for that is that now at the moment, due to the 3D structure of the device, the DRM design rule manuals and DRC design rule check rules are quite sophisticated comparing to the bulk CMOS. That means that the engineering team needs to spend some time to set the flow, needs to spend extra time to digest all the information so that they can apply those rules to their layouts, their physical designs. And there are some challenges like self-heating, which slows down the simulation times, gradient densities, and fixing the manufacturability concerns like EM electromigration or IR drop, etc. And at imec IC Link, we see that sometimes, I mean, we are doing 5 or 6 DRC loops so that we will have a DRC clean manufacturable layout at the end of the design. And on top of that, the PVT, process voltage temperature combinations, went up to 100 combinations. So you need to run all your timing and power closures against those 100 combinations, which adds extra time and extra resources. So what is the consequences then? All of these, complications and longer simulation times, etc. That means, first of all, it's a kind of longer learning curve, again, comparing to the bulk CMOS. And what we've been seeing is that kind of the design teams for a new node, 3 to 4 months of extra time for this learning curve. And also, since we are talking about, heavily processing the EDA tools, so you would need the massive CPU power, and you would need enough disk space utilization to store your output of your analysis. So most of the time, where do we spend the most of the time during the design? Well, first of all, as I said, to setting up the flow, the design flow. The second one is the multiple and lengthy and sophisticated iterations for timing and power closure. And finally, the physical verification so that you would get a DRC clean layout. Well, to overcome all these issues, actually, you don't need to generate this know-how internally at the first step or in the first development. That's why ARM and imec are here to help you with those designs, to help you to step up, to come up with your solution utilizing FinFET technologies in your SoC system. So next one is the project management and planning that I would like to spend a couple of words. So this is important, especially for the startups. Why? Because you need to set the expectations correctly to your investors and to your potential customers. From our experience, we see that you should expect like between 20% to 40% longer lead times for FinFET SoCs comparing to the bulk CMOS. And also on top of that, we always suggest an initial phase, introducing an extra initial phase. You could call it feasibility or de-risking phase, where we set the flow and clean the pipeline so that we will have a flawless chip development timeline. All in all, and maybe one more thing which is important, for such sophisticated projects, we always suggest to engage with the IP and EDA vendors as early as possible, so that you would not see, surprises on the way, so that you can mitigate the potential risks as early as possible. And I've been talking about the EDA tools that we are using for our development. Here you see it's kind of a complicated chart, but this shows the backend EDA tools with the required features listed here. So the left-hand side, you see this is the EDA tool set and the features for 40 and 28 nanometer. And by the way, for the bulk CMOS, you can use more or less the same kind of tool set. But when you go to the FinFET side, like 20 nanometer, 10 nanometer, and 7 nanometer, first of all, the number of the features, number of the runs, number of the combinations you need to execute is increasing, almost doubling. And at the same time, you can see that most of the time you may not be able to use the full EDA tool set that is developed for 20 nanometer that cannot be used, for example, in 7 nanometer, where you need to add extra features. So what does this mean? Two folds. First of all, yes, for those extra features, you need to add extra budget, which needs to be paid to the EDA tool vendors. And the second one is that since we are talking about multiple or extra features that needs to be run, you need to budget your timing accordingly. And again, as imec, we can help you thanks to our very good relationship with the EDA vendors, where we can provide some flexible offerings there. Another important point is the IP selection. It's crucial, especially the SoCs we have at the moment. So it is a crucial part of the design. We always suggest our customers to assign a dedicated team for all these, to achieve all these 4 steps I put here, like IP vendor selection, IP procurement. It's kind of a painful process, the IP procurement, because you need to involve your finance, your legal, your technical people, so that you make sure everything is fine. And also IP qualification, where you do your analysis based on your system, so that you make sure that this IP is the right IP. And the IP integration, where you integrate the hard macros and soft macros into your system. And the IP integration is not something that starts from T0 to T1, but most of the time it's a process that goes throughout the whole development flow, almost until the tape out. So this is kind of a crucial part of the overall development phase. So all in all these challenges we mentioned, okay, and there is some consequences on the cost. For the cost, I'll elaborate a little bit more. The contributor to those cost items is mainly the manufacturing and design and / the ADA parameters. For example, for manufacturing, for TSMC 28 nanometer, we're talking about, for a full mask, 45 to 50 mask layer sets based on the options you're selecting. But when you go to the FinFET, the number of those mask layers can go up to 80. And on top of that, it's kind of sophisticated mask sets. Another data point that I could give you, for a 16 nanometer full mask NRE for the mask layer generation is almost 2.5 times of the 28 nanometer. And for the design and EDA tools, I already mentioned about the consequences. Yeah, so the bottom line is this. So, okay, you're getting a very, very good performance, I mean, matchless performance from the power dissipation point of view, size the density point of view, speed point of view, and there is a cost to that comparing to the bulk CMOS. The bulk CMOS or the mainstream processes are still interesting. I mean, the market and the industry is using them heavily. But for the markets like, mid-end, mobile, automotive, medicine, IoT type of applications. But when you switch, if you're thinking switching to a high-end market segment, 5G, high-speed networking, AI kind of, then there is only one solution, that's FinFET. Well, to sum up, okay, it was always painful from switching from an older node to a newer node in the mainstream nodes. But switching from bulk CMOS to FinFET has its own challenges and constraints. I tried to elaborate those. So it's important to make this trade-off between performance and cost. So it should be done very wisely. As I mentioned, yes, there is a huge performance advantage, huge competitive advantage when you do things in FinFET. As written here, as I wrote here, we're talking about 60% faster, 50% more power efficiency, and almost halving the chip area that you're doing with, let's say, 28 nanometer. And these parameters are for 12 nanometer. So again, if you're targeting high margin, high volume, high performance market segments, then this is the way you should be going. And again, just to repeat, imec and ARM, we are here to support you guys in implementing your SoCs utilizing FinFET technologies from both the requirement spec and design point of view up to manufacturing, testability, and supply chain.